Oh hi! Welcome to the next video in our series on thermodynamics, and in this video we're going to talk about the very important notion of entropy. And entropy is intimately entwined with the second law of thermodynamics. And the second law really is the glue that ties together the zeroth law and the first law, so it's a very important rule. So in order to do so, it's good for us to recap for just a second what was found in the zeroth and the first law. Both of these make a statement about changing the state of a piece of nature, changing the state of a system. If I have a piece of nature here, again, could be a gas, could be a banana, could be a cat, could be the whole universe. If I have a piece of nature over here and I want to change its state, I want to change the numbers that define the system, right, like the volume or the pressure or whatever it is, then I can do two things. The zeroth law says, well, you can just place it next to another piece of nature, and if those two pieces of nature don't have the same temperature, then nature will make both of these systems change, and then you have a changed system. So you can change systems by putting it next to another piece of nature which has a different temperature. That was really the conclusion of the zeroth law of thermodynamics. But what one can also do, and that's the first law of thermodynamics, is you can start pushing and pulling on your system, and that will make the variables that make up your system change. You can get a different volume or a different pressure. And the first law then also told us that the total amount of change in the system, its energy change, du, is given by the sum of how much you put it next to some other system, how much the zeroth law did its work, that's this one, and how much you did pushing and pulling, that's this one. And just to recap finally the first law one more time, we also saw that it is completely non-trivial that the sum of these two things actually make up a definitive number, because this guy didn't by itself and this guy also didn't by itself, but their combination did. So that was really what the first two laws told us, the zeroth and the first law. Now in our video on the first law of thermodynamics, where we wrote down this for the first time, we came to an interesting realization, namely that if they can be added together to make up one final number, that means that they really are, well, the same sort of stuff. It's both of them, it's energy. Sure, the way that the energy is supplied to the system or taken from the system is different. This is energy that is supplied or taken away due to temperature differences with the surrounding. And this is energy taken or supplied by pushing and pulling, but they're both energies. And the question that we ended with in our last video was, okay, but if they are really the same sort of stuff, is it then possible to exchange some of the stuff, say the work, and turn it into heat, or to change the heat into work? And if so, if that is possible, by what amount can that be done? This is what the second law of thermodynamics will do for us. It will answer that question. It will tell us, yes, that can be done. It will also tell us how, by what amount it can be done. The number that's going to tell us by what amount that can be done, that number is going to be called the entropy, and it's going to be designated by the capital letter S for entropy. So we're going to investigate this in full detail right now. In order to do so, I'm going to have to introduce a system again. And just as I keep reiterating, the details of the system are not going to matter for our conclusions, but I need something to point at. So let's take the example of a gas. Why not? Replace it by a banana if so desired. If I have a gas, there we go. Here's a gas in a barrel again, and it has a pressure and it has a volume. Suppose, for instance, that I say, you know what? I am going to put another piece of nature next to it. You know what? I'm going to put my kettle here. The one that I use to make tea with, yes? If I want to raise the temperature in my kettle, one thing that I can do is, well, I can push down on that system. Then by my work that I'm now performing, these P and V will turn into new numbers, And those new numbers will, by the zeroth law of thermodynamics, change this system as well. And if I set it up in the right way, I can make the temperature of this guy go up and I have boiling tea. So apparently in my example here, I can use work to make, so this is work that goes in, and because of the changing of this system due to my work, I can make heat go from here to here and boil my water for my tea. So it seems that it is possible to make work go into heat and therefore a temperature raise. In fact, people who have a boiler at home, in just really in their apartments, a boiler where you get your water from that you take a shower with is not water that's constantly kept at 80 degrees Celsius. It's water that's kept under high pressure. This one here, the pressure pushing down, the work that is then turned into the raising of the temperature. So we know from practice that yes, you can actually turn work into heat. Can you do the opposite? Can you do the following, for instance? Here's my gas again. There we go. And suppose now that I take my boiling water again, but now the boiling water is much hotter than this gas is. So here's my boiling water, my kettle. Then it has a higher temperature than this. Then the zeroth law says, well, then there's going to be some heat exchange. So there's going to be some Q that goes from my hot water into the system. No pushing and pulling, it's just the zeroth law at work. And then these numbers will change. And if I set it up just right, I can make these numbers change such that V increases and my piston, my lid, will go up. And that's good because then I can use this raising of the lid to, I don't know, put to some machine, a train for instance, and make the train work. In fact, this is how steam engines work. This is how trains were made before the advent of electricity. They just use the zeroth law, turn it into work. So we know from experience that yes, you can turn heat into work and you can turn work into heat. So we know that the answer to the question, can you turn heat into work and work into heat, is yes. But we haven't quite answered the question yet by what amount. And let me foreshadow already a little bit. We are going to find that it is possible to turn work into heat. And you can even do it to 100%. You can turn all of your work into heat. But we will also find that it is impossible to turn all of your heat into work. You can turn some of the heat into work. That's going to be the heart of the second law of thermodynamics, and that's going to be ultimately the definition of entropy. And that's quite interesting because yes, heat and work are two things in the same bucket. They're both the same sort of stuff. They're both energies. But apparently nature has a preference for turning one of the energies into the other and not the other back into the first. You can make work turn into heat with 100% efficiency. You cannot turn heat into work with 100% efficiency. And nature, for some reason, doesn't seem to like this very much. So let's see if we can show that this is really the case, this statement. In order to do so, I am going to introduce a process. I'm going to, again, for sake of having something to point at, I'm going to take a gas again. I'm going to draw its PV diagram, the pressure of that gas as a function of its volume. And I'm going to let the gas go through a process. And by this process, I mean that I'm going to make the gas take up some heat from the surrounding and try to turn it into work and see if I can do this with 100% efficiency. Now, in order to do so, I'm going to need a cycle. I need the gas to go through its cycle where it absorbs heat from the surroundings and makes work, and then gets back to the original situation so it can do it again and again and again and again. Such a process is in thermodynamics called a thermodynamic engine or a thermodynamic process. So the word engine might make you indeed think of steam machines or locomotives back in the Old West or so. But I want to be very clear that, again, I'm just taking a gas as an example to point at. With thermodynamic engine, I don't literally mean a machine like a steam engine or something that contains a gas. It could be anything in nature. Just whatever process tries to take heat from the surrounding and turn it into work. A good example, for instance, will be photosynthesis. Yes, that's a thermodynamic engine. A plant takes up sunlight, which is a form of heat, and turns it into work because the thing will grow and move against gravity, which is pushing and pulling, which is work. So engine isn't just machines. The word connotation might be a machine, but engine is meant in the very broad sense of the word, a process that takes heat, turns it into work. Again, in my example, happens to be a gas. Okay, now let's make the following process happen. Let me draw it first. Here I have a gas that goes through 4 phases. And at the end of going through the 4 phases, it will go back to its original position, the original starting point. This particular engine is called an Otto engine. You can find many more of these engines in literature, but I just need one to make my point. So I'm going to take the Otto engine because it's relatively simple. So what does the gas do? Well, suppose that it starts at position 1. Then you can see that from position 1, which corresponds to a volume 1, so the gas is in a particular volume, it will go to position 2, which means, as you can see, that it will lower its volume. So the gas will become in a much smaller container to volume number 2. And the pressure goes from this number, pressure 1, to a higher number. This is typically what you would expect with gases, by the way, that if you compress them, you make its volume smaller, the pressure will go up. Especially, by the way, if you have an ideal gas, that you might know that ideal gases are gases that obey the following rule, that the pressure times the volume is up to a number equal to the temperature. Now you can easily see from this relationship that the P and the V are inversely proportional to each other, which gives it this graph. Now, if you don't like your gas to be an ideal gas following this particular law, that's fine. That just means that these arrows will have a slightly different curvature to them, but it doesn't matter for my example. Okay, so what I have here is a gas, I compress it, and it becomes in a smaller volume, and as a result, the pressure has gone up. That's this process. Let's call that process number A. It goes from 1 to 2. Now, from this point, it will go to point number 3, to state number 3. And as you can see, it stays at volume number 2. The only thing that will happen is that the pressure will go up, but the volume will stay the same. So it's a gas that I've pressed together. That's phase A, process A. But once it has come to its new volume V2, I keep it there. The only thing I do is raise the pressure in one way or another. And that gives us pressure number 3. This process is going to be called B. And then there is process C, which is just the opposite. It just means that I'm now going to make the container of the gas, the volume, going to expand again. I'm going to push out the lid, or let the gas itself push out the lid. And then that means that the volume goes back up again and the pressure will lower, possibly using this ideal gas law. If not, that's fine. It will still lower but via some different rule. And then we'll end up here. Point number 4, this is process C. And at the end, it's at state number 4. And then the volume is kept constant again, and just the pressure is allowed to go back to its original starting point. This is process D. This particular set of 4 steps, that is by definition called the Otto engine. Otto engine. Now, using our first law of thermodynamics, we can immediately assign where heat was applied and where pressure was applied. So here, for instance, well, let's start with process A. Volume has changed because you went from a big volume to a small volume. And if you recall from the previous video, making volumes bigger or smaller means that you had to push or pull on the system, yes? So obviously, but in process A, work was applied to the system, and I will call this work that we had to put into the system to make the change of volume happen. I'm going to call it WA. It's the work that it did at process A. This literally is just me pushing on the lid of the gas to make it go into a smaller volume. That's WA. In the same way, by the way, over here, if you go from 3 to 4, well, in process B, what you have done, you have raised the pressure, so the gas is starting to push back on the lid. You're just not letting it do it here, but in process C, you are letting it do it, and that means the gas itself will push the lid back up. And that means in process C, there's work coming out. It's the gas that pushes back the lid, and energy is supplied back to the universe, back to the environment, by the gas pushing back the lid. So there's work coming out, if you will. So that takes care of process A and process C. Process B and process D unfortunately are unaccounted for, but we can immediately see this is not due to work. Process B is not due to work. Process D is not due to work. Why? Because we saw in the previous video that work is related to a change in volume, right? Work was defined as minus pressure times dV. dV is a change in volume. But in process B, the volume doesn't change. It stays at V2. There's no change in volume. So there is a change of the gas, but it's not due to work. Same here. It goes from 4 to 1, but it stays at the same volume. So that means there is a change of the gas, but it's not due to work. So we immediately know that processes B and D must have been due to not work, but by the zeroth law. In other words, heat has come in. QB for the heat that went in at process B, and over here heat came out again. QD, the heat that came out at process D. So in this way, I can sort of understand the Otto engine. I haven't said exactly how I did things, but I have a pretty good idea now. Process A is me pushing on the lid. Process B is just making sure that it gets in contact with some other piece of nature such that heat will flow in by the zeroth law. Just means put a boiling kettle of water next to it. It will absorb some heat from there. Here the lid pushes back because of the high pressure that you built up in B. So that means the system, the gas, will give back work to the universe. And when you go here back down, that means that the system, the gas, will give back some of its heat to the universe. So you have this whole system. Okay, now, one thing I know, the sum of these four numbers is 0. This is the first law of thermodynamics. We know that the sum of the change in heat and the sum of the change in work it should give you the same number regardless of how you do it. That's the first law of thermodynamics. But the fact that you came back to the original starting point means that ultimately you haven't done anything to the system, so the total energy cannot have changed if you go through the whole cycle. So I immediately know the relationship between those four numbers. In fact, I can write it down right now because we're going to need it in a moment. du, that's the total change in energy of the system. Well, it's given by the amount of the total amount of work that is applied to the system, which is WA is what we put in, but you steal or you get out of it WC. So the total amount of work is WA minus WC, and then the zeroth law of thermodynamics, or sorry, the first law of thermodynamics tells you that you have to add the total amount of heat. And there you can see, well, there's heat that went in. That's QB, but there's also heat that came out, so the change in heat is all of this. So I'm really just applying now the first law of thermodynamics, the fact that the total change in energy is just the sum of how much work you did and the sum of how much heat you supplied. And the fact that you came back to the original starting point means that ultimately the system did not change, there was no change in energy. And in this way, I know how WA, WC, QB and QD are related, namely in this matter. This is the first law of thermodynamics. Now, what I would now like to do is ask myself the question, how much work can I get out of this? Remember, we were interested in the question, can you turn heat into work? So we need a number that tells us whether that can be done. That number, let me write it here, is this Greek letter eta, it means efficiency. And with efficiency we mean, well, if you look at all the work that came out and you divide it by how much heat you put in, that tells you how much of that heat has been turned into work. If that number is exactly equal to 1, that means all the heat that you put in has all been turned into work. So let's define that for a moment. The efficiency, again, is defined as, well, the total amount of work that you got out divided by the amount of heat that you put in. The heat that you put in is QB. Okay, that's the efficiency. Again, if this number is 1, that means that the total amount of work that came out is exactly equal to the amount of heat that you put in. In other words, that all the heat that you put in was turned into work. Now let's see if we can rewrite this a little bit, because we can. Because remember, here we use the first law of thermodynamics to turn some of these numbers into each other. QB is just QB, that's this number, the heat that went in. Omega total was the total amount of work that you got out, but of course you have to subtract the amount of work that you put in, right? So it's the work that you got out, but you also put some work in, and you're interested in the work that the total work that came out. So we're not interested, so we have to subtract the amount of work that you yourself put in. That doesn't count to what you get from the machine because you put it in yourself. So the total amount of work that you got out is the amount of work that came out in process C, well, minus the work that you had to put in yourself because you haven't gained that work. That's just what you put in. So this is why it's WC minus WA. And according to our first law of thermodynamics, WC minus WC minus WA is equal to QB minus QD. So if I now use the fact that this number is equal to that number, I can change WC minus WA into QB minus QD. This equality sign is what I put into my definition of efficiency here. And that now means that if I just do this fraction, I get QB divided by QB, which is just 1, minus QD over QB. So this formula will tell me how efficient my Otto engine is in turning supplied heat, QB, into a net amount of work that comes out. That's this formula right here, and to get that formula I needed the first law of thermodynamics. This is such an important conclusion that I'm going to write it one more time over here, so I have some extra space here in a moment for writing. There we go. This is the efficiency of the Otto engine, and as I was saying before, if I want all of my heat that came in to be turned into work, this number has to be exactly 1. But we can already see that it's not exactly 1, because it's 1 minus a little. How much minus is there? Well, it depends on how much heat is being thrown out again. The only way to make the Otto engine make all the heat be turned into work is if QD is 0. In other words, when there is no heat being thrown out at this point. Question, can that be done? The formula tells us I get a 100% conversion from heat into work at the moment that the machine, or the engine, my process, doesn't give any heat QD back to the universe. I hope that makes sense too, by the way. Because if it gives a little back to the universe, some of the heat that was put in also comes back out again, well then this heat is not available to be turned into work, yes? So clearly this has to be 0 in order for the engine to be 100% efficient. Can this be made 0? That's actually the question. It can't. I hope the reason is obvious. The reason is the 0th law of thermodynamics. Why? If you recall, process D meant that you went from 4 to 1, so you had the change of the state, right? The pressure went down, but it was not due to work because you did not do anything, no pushing and pulling on the volumes. But the only way, that's what the zeroth law tells you, for a system to change its state from 4 to 1 in this example, is to put it next to some other thingy that has a different temperature. So what I need in order for this to be 0 is to have the system have the same temperature as the surroundings. Because that's the only way that no heat will flow out. If there is a temperature difference between here and there, then the zeroth law says you will lose some of your energy. That's QD. If I don't want to lose any energy, this temperature has to be that temperature. But if there's no change in temperature, suppose that I do indeed make this temperature the same as here, so this QD would indeed be 0, I will get 100% efficiency, then my system would not change from 4 to 1 because there's only two ways to change the system. Either you do it by work or you do it by transfer of heat, but because I've made the Otto engine such that there's no work being done, if I also leave out the possibility of its changing state due to heat, because I want this to be 0, then it can never change its system. If I make the temperature here the same as there, it will just stay at location 4. There's nothing changing the system from 4 to 1. It has to be either heat or work, and since work, by the way that my Otto engine is defined, doesn't do it, it has to be by heat, so you will always lose a little bit over there. Otherwise, you will not go from 4 to back to 1. So the important conclusion that we can draw here now is that the efficiency of this Otto engine is necessarily smaller than 1. And that means it is impossible to turn all of the heat that went in into work. It simply cannot be done. That's the big conclusion based on the Otto engine. Now, of course, one example doesn't prove a whole claim. Yes? So the fact that I was able to show this for the Otto engine doesn't prove in the slightest that this is a rule that holds in other engines as well, other processes where things change. So this is really, if you want, an assumption. This is what the law of the second law of thermodynamics then tells you. It tells you that the fact that the efficiency of your engine cannot be 1, must be smaller than 1, that constitutes the second law of thermodynamics. So we've shown it for one particular case, but the claim is it's true for all cases. And people have tried and tried and tried some more, and no matter how they did it, either in the laboratory or by theoretical considerations as we were doing now, they just could not make it happen, so they turned it into a law. That's the second law of thermodynamics. The way that it's typically written is as follows. Here's one way to write that law that's going to be useful for us a little bit later. People typically schematically write the second law in the following diagram. This is the outside world. It has some temperature. Suppose that it has some H temperature. By H, it simply means higher than the low temperature that I'm going to do over here. So I have my engine, which is depicted here by a circle. Doesn't have to be a gas. This could be the banana again, or the universe. And it's connected to the outside world to a warm part of the outside world with a high temperature and a low part of the outside world with a low temperature. And then you know that the zeroth law says, oh, but if there is a high temperature here, if there's a temperature difference between the two systems, then heat is going to flow. So I'm going to call this QH. Heat will flow from the outside world into your engine. From your engine there might be some heat flowing back to the outside world, that's QL, and it turns the engine here, turns it into work. This is how you schematically write an engine. Now what does this second law tell you, as we saw in the Otto engine? All this energy that goes into your engine in the form of heat, cannot all of it be turned into work. Some of it is leaked back to the outside world, that's QL. Before that was what we called QD. So this is one way to write the second law of thermodynamics. It says in a process like this, it is impossible for QL to be 0. That's what the second law means. In fact, this formulation of the second law has a very special name. This is the Kelvin formulation of the second law of thermodynamics. It means that if you steal energy from the outside world by sucking in heat by temperature difference, you can turn it into work, but there will always be some energy that is not turned into work, and it will be given back to the rest of the universe, just like in our Otto case. So the fact that QL is not 0, that's the second law of thermodynamics. Now if you would open up your books on thermodynamics, you might find that there is another way of writing the same law of thermodynamics, and it looks different. So let me write down the other one as well, so you have seen them both. So forget about this one for now. I again am going to take some engine, circle, and I'm going to connect it to the outside world with a high temperature, TH. And again, I'm also going to connect it to a piece of outside world with a low temperature, TL. Here's another formulation that you can find in the books, and that's the following. It says that if you want heat, QL, QH, if you want it to flow from the low temperature to the high temperature, then it can only be done if your engine takes in work. The other way is quite simple. You can easily make an engine or some process that sucks in heat from the outside world and just brings it back down, gives it back to the universe in a low temperature. In other words, heat flows automatically from high to low temperature. That doesn't cost you any trouble. But if you want to make heat flow from low temperature to high temperature, that's this process, you have to do work from the outside. Now, this might not be surprising to you, because if you take a cup of tea and you put it in a room that has a lower temperature than a cup of tea, it's going to be the cup of tea that's going to cool off. It's not going to be the room that heats up. In other words, energy from the tea is going to flow into the room. In other words, it will go from the hot thing, the tea, to the room, and the energy will flow in the form of heat in this direction. If you want to do it the other way, that you have a cup of tea that is hotter than the room, yet it sucks in energy and heats up even more, that will be this process. And I'm sure everybody who's ever had a cup of tea has noticed that indeed things do not heat up if it's already the hottest thing in the room. So in that sense, this is not surprising, yes? I mean, this is just everyday experience turned into a law. So to be sure, you can make things that are hot even hotter. The only thing you have to do is you have to work on it. You have to perform work that you have to put in from the outside. This is also a formulation of the second law of thermodynamics, and this one is called the Clausius formulation. So the Clausius formulation says it is impossible for an engine to suck up heat from something that is low temperature and bring it to a high temperature without you doing work. So in other words, the Clausius formulation of thermodynamics says this process where heat goes from the low to the high can only be done if you supply work from the outside. That's the Clausius formulation. And this is what you encounter in many books. So we have two formulations right now. Two formulations. Now, which one is it? Right? I mean, we were talking about the second law of thermodynamics, yet we have two different formulations, and they sort of look the same because they all have something to do with heat flow and work, but they don't look quite the same. It turns out that these two formulations, Clausius and Kelvin, are mathematically exactly the same formulation. You have to puzzle a little bit, but you can mathematically show that if this is true, then this must be true, and if this is true, then this must be true. In other words, they're completely equivalent. I'm not going to show you the proof. I will leave that for your dedicated course in thermodynamics, but trust me when I say that this can be mathematically shown to be the exact same thing. So if you open up your books on thermodynamics and you find the second law of thermodynamics, you can sometimes see it applied in this form, the Kelvin form, and sometimes in the Clausius form. Don't worry, it's all the same thing. Okay, now that's all clear enough. Here is where I'm going to ask the following question. We have seen now by the Kelvin formulation of the second law that it is impossible to turn all heat into work. And the question that you can then ask is, okay, if I cannot do all the heat into work, can I at least have some of the heat turn into work? And how much is that? Is there a cap on it? And that question also was on the mind of a French engineer who served in Napoleon's army. His name was Carnot, and Carnot came up with a very ingenious way of answering this question, and the answer is going to be extremely important to us. He said, well, let's introduce a cycle, an engine. It's now called the Carnot engine. And he says it's again some process, some system, could be a gas, could be a banana, but something that sucks up heat from the outside world and turns it into work. And of course, as we saw in the Kelvin formulation, that means some heat will flow back out of the system. You cannot perform it 100%. But he says, let's envision a process, an engine, that is what we call reversible. By reversible we mean, I'm going to draw it here, but in a moment I'm going to need another engine to prove a very important point. So let's focus on here. Here is an engine, I put a C in there, by which I mean Carnot engine. Here's the outside world with a high temperature, here's the outside world with a low temperature. Carnot asked himself the following question. He said, suppose that I have a cycle that can be reversed. So the cycle will always, like all engines, will always look like this. Some heat, I'm going to put primes on there because this is the one that I'm going to use without the primes, but the idea now is I have some outside world, is going to suck in some heat from the outside world due to high temperature, turns it into work, but there will be some leftover, and as we saw, the Kelvin formulation of the second law says that this number cannot be zero. You will always have some energy being spilled away and not be turned into work. Carnot now said, let's envision that one can make an engine that also works the other way around, where you can reverse the arrows, if you will, so that you can do this. So it's the exact same engine, just running backward in time. It steals from the low temperature, turns it into high temperature. Remember, according to the Clausius formulation of thermodynamics, that means you need work. And Carnot just says, I'm going to take one of those engines and just let it go in reverse. And then it will look like this. Okay. Now this guy, this Carnot engine, will have some efficiency. If you recall, the efficiency was defined as the amount of work divided by how much heat you took in. In the original one, the heat that went in was called QH. That was before I reversed the arrows. And then work came out, and this was how we defined efficiency beforehand, yes? So it's the amount of work that comes out divided by how much heat you took in. So this is the efficiency of the Carnot cycle before I reversed it in time. Okay, so here's the Carnot cycle efficiency. Now let's have another engine here. For instance, the Otto engine. Doesn't matter, could be any engine. Let's make it the Otto, why not? And the Otto engine will, of course, also schematically look like this. It will steal some heat from the high temperature, turn it into work, and there will be some leftover heat that will be given back to the universe, to the environment, and the Kelvin formulation says this cannot be zero. Alright, all clear. Now this guy will also have an efficiency, which in this original formulation will be the amount of work that comes out divided by the amount of heat that you took from the universe. So that's this guy again. So we have two engines now. Some non-Carnot engine and a Carnot engine. And the Carnot engine, by definition, can be reversed in time. So the arrows point in a different way. Now Carnot, the guy, the engineer, came with a brilliant realization. He said, you know what? If I just take these two engines and I squeeze them together, I can make one big engine. This is what I'm going to, oh, this one doesn't work. I'm going to make one big engine. That's this one here, in red. And I'm going to look at what this big engine does. So what he really did was, he says, you know what, I'm going to take the work that comes out of my non-Carnot engine and I'm going to use it to put into my Carnot engine, my reverse Carnot engine. So this work is direct, so this work that comes out of this machine is directly fed into this machine. And why was this such a brilliant idea by Carnot? Because this whole system in the red can now be summarized, I'm going to do this here, as just one red engine, which has a very important property. Let's look at it now. So let me be consistent in my notation. Here is the red engine, which is just the combined of these two together. And let's just count how much heat comes in and how much work comes out. So this is the combined non-Carnot and Carnot cycle put together. Here's TH, here's the environment TL. Now, first of all, let's look how much how much work is being produced by this combined engine. The answer is none. Because look, all the work that was made by this engine was fed into the Carnot engine and nothing comes outside of the red box. So in other words, the combined engine doesn't have any work output. Okay, sure. Let's look at how much heat is being transferred between the high and the low temperature. Well, let's do it here. Let's count how much heat is being taken from here into the combined engine. Well, it's just a matter of counting, isn't it? This part of the machine took in QH from the outside world, but this one gave back QH primed. So the total amount that was taken from the outside world and going into the machine is the difference between QH, this one, and QH primed, that one. So this combined machine takes up this amount of work from the environment. Now we can also then ask, okay, but how much is then being given back to the universe? By the first law of thermodynamics, you can already tell the answer. It's the exact same amount. Yes? Because if nothing comes out in the form of work, then the first law of thermodynamics says that all the energy that came in should in its totality come out again. So I don't even have to look at it in detail. I know that the amount that comes out is the exact same number. Okay, all clear. So Carnot realized that his hypothetical Carnot cycle, when run backwards in time, combined with a non-Carnot cycle together, is equivalent to this. All of this is just this combined engine. It says you steal energy in the form of heat from here and bring it all the way to there. But this comes with a very important conclusion, because it means that QH must be a bigger number than QH primed. This is extremely important, because if QH is a bigger number than QH primed, that means that the total amount of energy in the form of heat is flowing downward. If QH primed would have been a bigger number than QH, then this total number would be negative, which means that the machine would have sucked energy from the low temperature back up to the high temperature. And Carnot realized this is not allowed, because the Clausius formulation of thermodynamics says you are not allowed to steal energy from low temperature and bring it to high temperature. You can only do this if you put work in it, but there is no work on this combined machine. So we know from the Clausius formulation of the second law of thermodynamics that this must be true. QH is a bigger number than QH primed. So that's a big conclusion that Carnot reached. Now, since we know that, we can go back. This was the efficiency. So I'm going to split those two machines back away from each other again. So I'm going to look at them as separate machines again. Each came with an efficiency. This is the efficiency of the non-Carnot cycle. This is the efficiency of the Carnot cycle. And we can now see which one of the two is bigger. Because the amount of work for both is the same number. Yes, this work is that work. So the works, the numerators are the same. But according to this conclusion by Carnot, this number, QH, for the non-Carnot cycle, the denominator is a bigger number than this number, QH prime, for the Carnot cycle. So you have two fractions here, which has the same numerator, but a different denominator. And this denominator is bigger than this denominator, and as a result, this efficiency is a bigger number, is a smaller number, because you divide by a bigger number than the Carnot efficiency. This is the conclusion that Carnot reached. So, it says that if you have an engine, doesn't matter which one it is, any engine will always have an efficiency that is lower than the Carnot efficiency. The Carnot cycle is the most efficient in turning heat into work than any other cycle that there is. This is the big conclusion that Carnot reached, and this is why the Carnot engine is so important. It's the hypothetical engine that is the best that nature allows in turning heat into work, and we have now mathematically proven that. So it's well deserved that the Carnot engine carries the name of this very brilliant man who devised this ingenious way of looking at it. So that answers the question that we asked at the beginning of this video. Can one turn heat into work? The answer is yes, any engine can do that. But can you do it maximally? Can you turn it 100%? That answer is no, by either the Kelvin or the Clausius formulation of the second law of thermodynamics. And then the subsequent question is, okay, but if you cannot do it 100%, what is the most efficient that you can do? And that is the Carnot efficiency. Any engine will always have less efficiency of turning heat into work than the Carnot engine. Now, there's a series of mathematical steps that I'm skipping here that you can do if you follow the proper course in thermodynamics, but you can prove that if this, what the maximum efficiency is, this Carnot efficiency. And without proof, I'm just telling you that this maximum amount that we've proven that exists is given by this low temperature, right? That's the temperature of the environment where you give your energy to, divided by the high temperature. So let me draw one more time an engine. There you go. It steals heat from the high temperature environment, turns it into work, leaves some of it, gives it back to the low temperature environment. And Carnot showed that the maximum amount that you can turn this into this is given by 1 minus the ratio of these two numbers. Again, this step, that the maximum Carnot efficiency is given by this formula, I'm leaving for your course in thermodynamics. So, that's the second law of thermodynamics. One can turn heat into work in two formulations, Clausius and Kelvin. There's a maximum efficiency shown by Carnot, and that maximum efficiency is given by this number. Now it's very tempting now to say, but you know what, I can make this 100%. The only thing I have to do is make this part 0, because then I get efficiency is 100%, minus nothing, 100%. Now, if you want to make a fraction be 0, then TL has to be 0. In other words, the environment in which you place your machine, your engine, your process needs to be 0 temperature, absolute 0. So it looks as if you can make 100% efficiency conversion of heat into work, if only you would place your process in a 0 temperature environment. So it seems on paper as if this is possible, but here is where the third law comes in. I promise I will not talk too much about the third law. I will just briefly mention it, and I'm going to do this now. The third law of thermodynamics says that absolute 0 cannot be achieved in a finite number of steps. So if you have an environment, like this guy over here, and you want to bring it down to 0 temperature, then you have to perform things on it. Maybe you have to do work, maybe you have to extract some energy by heat. No matter how you do it, you will never make it exactly equal to 0. You can get very close, but not exactly 0. So if you trust that from me that that third law really is true, then that means that TL cannot be made 0. And that means that even the best efficiency that nature has in store for us can still not be 100%, even if you make the environment optimal. So, if somebody now comes to you and he says, I have a machine that can turn heat into work and it does it with 100% efficiency, you have to be very mindful, because he might be selling you 3 things that are wrong. First of all, if the machine gives you more work than it stole from the environment in heat, it means the first law is broken, because the machine cannot make more energy. It can only be, at most, hopefully, the energy that it stole in the form of heat. The second thing you have to be mindful of is that the Carnot conclusions say that even if the total amount of energy is conserved, not all of it can be turned into work. And even if that is the case, yes, then you have to go to absolute 0, which is not allowed by the third law of thermodynamics. So here's 3 reasons why you should not trust somebody who comes to you who says that he can make energy out of nothing. You're breaking 3 laws of thermodynamics there. So that is, in a nutshell, the second law of thermodynamics. Now notice that I have not mentioned yet the word entropy. So let me conclude this video by saying something about this entropy. We've seen now 2 formulations of the second law of thermodynamics, the Clausius and the Kelvin. And if you looked at the examples carefully, you saw that in both cases it had something to do with dQ, the amount of heat that you steal from the environment, and that it was related to temperature. The efficiency was related to temperature. Now, according to the first law of thermodynamics, there you go again, to the first law of thermodynamics, dQ you can read as the energy that you cannot turn into work anymore, right? The fact that we just saw before that there is always some heat that is not being turned into work means that there should be some function that counts how much of this heat cannot be turned into work anymore. So we should be able to write dQ here in terms of a new function that counts how many of the heat is already lost to be turned into work. And the examples show that it is related to temperature, because our conclusions were very heavily temperature related. Now I'm skipping a couple of steps here, but again it's too big of a topic to do full justice here, so let me just go through the conclusion. The fact that not all heat can be turned into work can be expressed in a new function. S is called the entropy, but which really counts how much of the heat is not available for work anymore. The bigger S becomes, the more energy is stored into Q, and the more energy is stored into Q, according to the second law of thermodynamics, the less you have for work. So this is entropy and is related to the temperature. This defines entropy. The amount of entropy change is defined as the amount of heat not available anymore to do work divided by the temperature at which you want to do the work. This is entropy. Now, since we saw that engines will always have some energy not being turned into work. With every cycle that will increase and will increase. With every time you go through the Otto engine, go from point 1 to 2 to 3 to 4 back to 1, you have lost some of the heat that cannot be turned into work anymore. So that means that as the entropy as a function of time becomes a bigger number. With every cycle you have less energy available to do work because more of it has gone into heat that it was dissipated back to the universe. And that gives us our third and the most familiar formulation of the second law of thermodynamics. It says that the entropy as a function of time, so here's how much the entropy changes in time, is bigger than zero. Entropy, with every cycle, we become bigger, bigger, bigger. You have less and less energy available to do work. So we have the Clausius formulation of the second law of thermodynamics, you have the Kelvin formulation, and you have the entropy formulation. You will have less and less energy available to turn heat into work. In other words, you have a bigger and bigger and bigger entropy as you go along. So that wraps up our introduction to entropy and the second law of thermodynamics. I want to make one final comment before we wrap up. Sometimes when you open up books on thermodynamics, especially popular science books, you'll find a slightly different definition of entropy. Entropy is sometimes defined as the amount of disorder in a system. The amount of chaos sometimes you read. That is specifically wrong because chaos already has a designated meaning, but in everyday speech sometimes you hear that the second law of thermodynamics says that entropy is chaos or disorder. Now there is some grain of truth to it. In fact, entropy, Boltzmann found out, Ludwig von Boltzmann, a scientist in the late 1800s, found out that this function entropy can actually be written as follows. That this entropy that we've just defined here actually has a formula. And that's this formula right here. Now what does it mean? Well, there's a KB over here, that's just a number, we don't have to care about that. The most important thing is omega here. Omega has to do with the microscopics of the system. You see, if I have a system and it consists of, say, particles like a gas is or a cat or a banana is, then the system has a pressure and a volume and all these other observables, but those are macroscopic. And you can switch around some of the particles in that system. If I take a banana and I take two of the banana particles, my colleagues in chemistry would hate me if I say banana molecule. If I take two of the particles in banana and I swap them around, so the microscopic parts of the banana I swap around, from a distance where I only see the macroscopics, the banana will not have changed. It will still have the same pressure, it will still have the same volume, it will still have the same color, etc. So Boltzmann realized that entropy can be read as the amount of ways that one can swap around particles in a system such that the macroscopic features of the system are still the same. This number, omega, is the amount of swapping you can do. So the more particles you have, and in the more rearrangements that you can do without changing the macroscopics, that is called omega. Well, that is usually a very big number because a banana consists of many particles, so there's many ways to flip them around. And you take the logarithm of that big number, gives you still a very big number. You multiply it with something that is now called the Boltzmann constant, and he showed, Boltzmann, that the number that comes out is actually the entropy that we defined in a macroscopic way. So if you ever see entropy being defined as the number that counts in how many ways you can swap a system, then I hope you understand it's really just the same thing as we were doing macroscopically. And I hope you then also understand why it's called a disorder. Because the amount of way that you can arrange things means that the thing is highly disordered. If you have your very messy room and you have two pieces of mess and you flop them around, it will still be a very messy room. So the more messiness you have, the more ways of flopping around things, is directly related to a big number for entropy. So this is why if you make the connection to microscopics, sometimes entropy is named the amount of disorder of a system. With that, we have gone through all of our videos and we have seen the first 3 laws of thermodynamics and slightly a little bit about the 3rd law. For the people who are interested, I'm also going to record a video where I'm going to use these formulas to actually prove a couple of famous formulas in physics that you might have seen before, but usually derived from using only microscopics. I'm talking about the ideal gas law, and there's the Stefan Boltzmann law from quantum mechanics. If you don't know these laws, don't worry about it. They're part of different courses. But if you know these laws, then you've probably seen them derived by using bouncing particles in case of the ideal gas law, or quantum mechanics in case of the Stefan Boltzmann law. What I will show in my bonus video is that if you take these rules and you apply them to systems, you automatically get the ideal gas law and you automatically get the Stefan Boltzmann law, even if you don't even look at the microscopics. You don't know that there's bouncing particles. The laws of thermodynamics will give you those rules even if you don't know what's microscopically going on. And this is what I promised in my introductory video. Thermodynamics gives you laws and relationships between physics even if you don't know what's going on microscopically. So for the people who are interested in seeing that happen in quantitative detail, go to my bonus video and I will show you the derivation of the ideal gas law and Stefan Boltzmann law without using microscopics. With that, thank you very much for your attention. I hope you enjoyed it. I certainly did.